2.4 Lesson 2, Continuity and Discontinuity. Our objective for today is this one here. Number one, we have this piecewise defined function g of x. It is defined as 9 minus x squared for values from the domain that are less than 2, and it is defined as some constant k times x for values from the domain that are greater than or equal to 2. So we have a piecewise defined function, and the transition point is at x is equal to 2. So I just added that to the vocabulary. Transition point is where the rule for the piecewise defined function changes. So you'll notice that there is a constant k that's in the rule, in the second rule for our piecewise defined function. And this constant k can be whatever value you choose it to be. But a particular value of k will make the two pieces connect. It will cause the piecewise defined function to be continuous at x is equal to 2. So our objective for today is to find that particular value of k that would cause these two pieces to connect and cause the piecewise defined function to be continuous at the transition point x is equal to 2. So our objective is find the value of k that would make g continuous at x is equal to 2. And what that means is the two pieces will connect at x is equal to 2. So we will look at the definition of continuity, and we will be working with one-sided limits to find the value of k that would cause the function, the piecewise defined function g to be continuous at x is equal to 2. So let's go ahead and take a look at certain values of k. So what I'm going to show you now is the following. I'm going to show you the graph of this piecewise defined function for certain values of k. I'll first show you the graph of the piecewise defined function when k is 1. So I've entered my piecewise defined function into Desmos, and the syntax is you use braces, and then you have your condition when x is less than 2, colon, you enter the rule for that portion of the domain, 9 minus x squared, comma, and then you have the condition when input values are greater than or equal to 2, colon, and then you enter the rule 1x, close braces. So that's how you graph piecewise defined functions on Desmos. How do you enter greater than or equal to? You enter greater than first and then equal to after that, and it will turn into greater than or equal to. So I did this on Desmos, and I was able to graph this piecewise defined function with, of course, k is equal to 1. And you can see that the two pieces do not connect at x is equal to 2 at the transition point. So we have what we call a step discontinuity. This is a non-removable discontinuity. What does that mean? You can't fix this unless you change your function. So we call it non-removable. But in this problem, we are actually going to change our function to try to fix it. So don't get confused between this being removable or non-removable. The function that you are looking at has a step discontinuity. It's a non-removable discontinuity. We're actually going to change the function to try to fix this. So that's why we consider it non-removable, because we're actually going to change the rule here to try to fix it. So the next thing that I'll show you is what happens when I change this rule to 2x. So I'm actually going to change my function. So I'm going to make this 2x, and let's look at the graph of that. So when you change the rule for the second part of the piecewise defined function to be 2x, this is the part of the graph that you get that I will now highlight in gold. So it's getting closer to the first piece, but we still have a step discontinuity. So we're thinking, what should k be so that we will have continuity at the transition point of x is equal to 2? Well, we tried 1, it didn't work. We tried 2, it didn't work. Let's try 3. So we have a step discontinuity. It's non-removable, but we're actually changing the function. So we're now looking at a different function. So that's the difference between a non-removable discontinuity and a removable discontinuity. In a non-removable discontinuity, there's nothing you can do unless you're willing to drastically change your function. In a removable discontinuity, you just define the function to be a different output value only at a single input value where you have the discontinuity. So let's take a look at what happens when k is equal to 3. So for values of x greater than or equal to 2, we now have the rule 3x, and this is the graph that you get that I'm now highlighting in gold. So when we had 2x, I had this graph that I am now going to highlight in maybe black. And when we have 3x, we have the graph that was highlighted in gold. Maybe we should try something between 2 and 3, like 2.5. Let's see what happens then. So I'm going to change my function, make k equal to 2.5, and let's look at the graph. You can see now that this is the graph that I get for the graph of the function y is equal to 2.5x that I will now highlight in gold. And you can see that now at the transition point x is equal to 2, where the rule for my piecewise defined function changes, with k equal to 2.5, the two pieces actually connect at x is equal to 2. So the other piece is always the same, 9 minus x squared, and I'm highlighting that now in, to make it easier for you to see, I'll change it to red. And you can see that the two pieces connect at x is equal to 2. So this is the value of k that would cause my piecewise defined function to be continuous at the transition point x is equal to 2. So I wanted to have you see this visually first before we look at it using the definition of continuity. So we expect that when k is equal to 2.5, the function g of x will be continuous at the transition point x is equal to 2. So now let's go ahead and do this using the definition of continuity. So here's the definition of continuity that we learned yesterday. So we want to make sure that our piecewise defined function g is continuous at the transition point where x is equal to 2. So yesterday we looked at the definition of continuity. So how do we make sure that a function is continuous at a particular point? In our case, at x is equal to 2. We have to make sure that all three of these things are true. So we have to make sure, number one, that the function is defined at x is equal to c. So is our function g defined at x is equal to 2? The answer is yes. G of 2 will be, you use the second rule when x is equal to 2, and it would just be k times x, whatever k might be. And of course, we're trying to find what k should be. So now we look at the second question, or the second condition from the definition of continuity. So we have to make sure that our function has a limit as x approaches c, as x approaches 2. So we have to make sure from the second condition for continuity that the limit of g of x as x approaches the transition point 2 exists. How will we make sure that happens? Make sure you are aware that we actually have two different rules for the function g. One if the input values are less than 2, and a different one if the input values are greater than 2. So you have to consider what's happening as x is approaching 2 from values that are less than 2, and you also have to consider what's happening as x is approaching 2 from values that are greater than 2. So what that means is, to determine whether this two-sided limit exists, we have to use one-sided limits. So we have to examine the limit of the function g of x as x approaches 2 from the left, and we have to examine the limit of the function g of x as x approaches 2 from the right. And then we have to make sure that the one-sided limits exist and are equal to each other. And if we can show that to be the case, then we will know that the two-sided limit will exist and will be equal to the same value. So to make sure that the second condition from the definition of continuity is satisfied, I need to work with one-sided limits. So how do I make sure that the limit of g of x as x approaches 2 exists? As we just went over, we need to work with one-sided limits. So now we're going to take a look at the limit of g of x as x approaches 2 from the left and the limit of g of x as x approaches 2 from the right. And we've got to make sure that those two one-sided limits exist and are equal to each other so that the two-sided limit necessary for continuity will exist. So we're going to look at the left-sided limit of g of x and then the right-sided limit of g of x as x approaches 2. So if x is approaching 2 from values that are less than 2, we're in this part of the domain. X is less than 2, so we use this rule for the function g. So we're going to write the limit of 9 minus x squared as x approaches 2 from the left. And you can use the limit laws that we learned about. So you can write 9 minus x squared as 9 plus negative x squared. And then you can write this as the limit of 9 as x approaches 2 from the left plus the limit of negative 1 times x squared as x approaches 2 from the left. And then you can use, for example, the constant rule for limits, and the limit of the constant function 9 as x approaches 2 from the left would be 9. So you're going to write that's equal to 9. And then you can do something here where you rewrite this as negative 1 times x. So you're going to have plus the limit of the constant function negative 1 as x approaches 2 from the left times the limit of the identity function x as x approaches 2 from the left times the limit of the identity function x as x approaches 2 from the left. So what am I using? I'm using the product property of limits. I have negative 1 times x here. So I use the product property of limits to rewrite that as a product of 3 limits. And then this one here is a constant function. Negative 1 is a constant function, so that'll be negative 1. And that's the property for finding limits of constant functions. This is the identity function. So if x is approaching 2 from the left, the limit of the identity function will be 2. And the property for that would be the limit of the identity function. And same thing here, 2. So we have 9 plus negative 4, which will be 5. So now we have to look at the limit of the function g of x as x approaches 2 from the right side of 2. So if x is approaching 2 from the right side of 2, the input values are greater than 2. So I will use this second rule for the function g, and that will give me the limit of k times x as x approaches 2 from the right. And k is a constant, and we have x, which is the identity function. And we have a product here, so we can write that as the limit of k as x approaches 2 from the right times the limit of the identity function x as x approaches 2 from the right. So this is using the property of limits, or the limit law, for finding the limit of a product of two functions. So limit of a product is what we're using. And then we can use the limit of a constant function. For a constant function, when you find the limit, the limit will be just the value of that constant. And for the identity function, when you find the limit will be just c. So we will have k times 2. So the limit, the right-sided limit for the piecewise defined function g of x would be 2k. So again, what is it that we're trying to make sure? We're trying to make sure that the second condition from the definition of continuity is satisfied. We're trying to make sure that the limit of the function g of x as x approaches 2 exists. But we need to look at one-sided limits because x is equal to 2 is the transition point between these two different rules for the function g of x. So we've looked at the left-sided limit, which is equal to 5, and we've looked at the right-sided limit of the function g as x approaches 2, and that's equal to 2k. And according to the property for one-sided limits, the two-sided limit that we want to make sure exists, it will only exist if the one-sided limits exist and equal each other. So our next step is to make sure that we set the one-sided limits equal to each other, and that would allow us to solve for k. So we set the limit of g of x as x approaches 2 from the left equal to the limit of g of x as x approaches 2 from the right. So the limit of g of x as x approaches 2 from the left is 5. The limit of g of x as x approaches 2 from the right is 2k. And now we can solve for k by dividing both sides of this equation by 2. So we get k is equal to 5 divided by 2, which is of course 2.5. And when k is equal to 2.5, if you go back to condition number 1 from the definition of limit, what would g of 2 be equal to? Well, g of 2 would be equal to k times x, right? You're using the second rule to evaluate g of 2. Now that we know k should be 2.5, g of 2 would be 2.5 times x. 2.5 times 2 would be 5. So g of 2 would be 5. So what would be the limit of the function g of x as x approaches 2? Well, it would be 5. If k is 2.5 and you substitute 2.5 for k here, 2 times 2.5 is 5. The left-sided limit at 2 would be 5, and the right-sided limit at 2 would be 5. So the two-sided limit of g of x as x approaches 2 would be 5. And the value of the function g at x is equal to 2 would be 5. So what we just said would also make sure that the third condition from the definition of continuity is satisfied, because the limit of the function g of x as x approaches 2 is equal to 5, and that is equal to g of 2, which is also equal to 5. So we will have 5 is equal to 5, and all three conditions from the definition of continuity would be satisfied at x is equal to 2 when we choose k to be equal to 2.5. So the most important part of this particular problem was just to make sure that the limit of the function g of x as x approaches the transition point 2 exists. And that happens when you make sure that the two one-sided limits exist and are equal to each other. And you can verify that conditions 1 and 3 will also be satisfied, but this is what you really need to do. So to summarize our work, we looked at one-sided limits to make sure that condition number 2 from the definition of continuity is satisfied. And we set the two one-sided limits equal to each other and found that the one-sided limits will agree when k is equal to 2.5. That would make sure that the two-sided limit exists. And then you can verify that g of 2 would be equal to k times x. If k is 2.5 and x is 2, then g of 2 would be equal to 5. The two-sided limit as x approaches 2 would also equal 5. So all three conditions from the definition of continuity would be satisfied for the function g of x at x is equal to 2. If you choose k to be 2.5. The limit of g of x as x approaches 2 will be equal to g of 2 as well. So what that means is you would get this graph for the piecewise defined function, where at x is equal to 2, the transition point, the function would have continuity, because all three conditions from the definition of continuity would be satisfied. One thing that I would like to point out is this. The function y is equal to 9 minus x squared, when you graph it, you get a parabola. And if you graph it on the entire real line, the domain would be all real numbers. And this function is continuous. And the function y is equal to 2.5x, it's just a line. Let's say you graph this function on the entire real line. You would just have a line. So what I'm trying to say is, if you have y is equal to 9 minus x squared, the graph would be a parabola. And let's say you don't stop at x is equal to 2 and you keep going. And if you have y is equal to 2.5x, the graph would be a line. And let's say you don't stop at x is equal to 2, but you keep going. It would look like this. Both of these functions are continuous on their domains. Let's go back to the definition of continuity that we looked at earlier. All three things have to be true. And look at number 3. That basically incorporates number 2, and it also incorporates number 1. So when you have a function that's continuous at a particular x value, this has to be true. The third condition from the definition of continuity. And let's take another look at what it says. It says the limit of the function as x approaches c must be equal to the function evaluated at c. So I could have used that, and I would not have had to use the limit laws to do my limits when I was doing the one-sided limits, because I know 9 minus x squared to be continuous on its domain, and I know k times x to be continuous on its domain. So by the definition of continuity, I can evaluate the limits here and here just by doing what we call direct substitution. And that means you don't have to think about the limit laws to evaluate the limit of a function as x approaches c. If you know your function f to be continuous at c, you can just do direct substitution. So that's something that I wanted to mention in addition to the work for today's lesson. So today we looked at our piecewise defined function, and we were able to find the value of the constant k that would make the function g continuous at the transition point x is equal to 2.